Okay, I'm going to briefly describe some exploratory work that we're doing, which combines the type of simulation that you're looking at with SimPy on this course, and then with what we call reinforcement learning methods or reinforcement learning agents, which you'll also hear a bit more about later in the course. And these are agents that can learn to take actions and control things. So we base ours on the DeepMind methodology from Google. They're agents that can learn to play chess or drive cars, play other games. In our case, it's learning how to control a hospital environment, which you'll see as we explore this. So first of all, we need to talk about Q, because a lot of the methods use this concept of Q. Now Q, if we define it, is the expected long-term rewards for taking a particular action, which is a bit abstract. So let's have a look at an example. Example actions would be, well, we might open up more staffed beds in our hospital, though that may take time, or we might reduce the number of staff beds in the hospital, and that will also take time to implement. Our example rewards could be, well, we have a positive reward whenever we assign a bed to a patient. That's good, isn't it? But we've got negative rewards for unused beds because our accountant's getting grumpy about that, and we have a negative reward if you ever have a patient waiting for a bed because your doctors get grumpy about that. A notion also built into these methods is we say Q is discounted over time. What that means is that next month, next year matter, but today and tomorrow matter more. In fact, today matters the most, tomorrow matters next, and then over time it's important, but the importance reduces. And finally, Q is learned, so we give them no rules, these agents, what to do. They learn by trial and error. So they need to explore, trying different actions. And then they need to balance that with exploitation, doing what they think is best from what they've learned so far. And exploration in the real world can be risky. So there is also a concept, can you learn reasonable behaviour in a simulation and then transfer that to the real world to refine further learning. This is sometimes called sim to real transfer. So here's our basic structure. On the left we have our deep reinforcement learning agent, and on our right we have the environment, which may be real, or in our case it's a SimPy hospital environment. Now the agent observes the environment, so it gets what's called the state S, and from that observation it decides to take an action. A passes that action to the environment, and then the environment passes a reward back, R. And what the agent has got to learn to do is, given any observed state S and given what it's already learned, what action should it take to pass to the environment to maximise how R accumulates over time. Now, our first experiments are focused very much just on the interface, really getting the methodology set up between how do we create a SimPy simulation and build that in such a way that it interacts with these reinforcement learning agents, particularly agents that have already been built or at least very fully described that we can recreate. So we're using a simple hospital bed simulation to begin with. It has fluctuation in demand, weekly demand patterns, fewer patients coming in at the weekends, more in the week, and also the expected randomness. And then we send a negative reward back for beds without patients and also patients without beds. And the agent can change staffed bed numbers each day. It can say, I want so many changes to be implemented in units of 5, up to I think plus or minus 20 beds. It can ask for change in a day. But those changes take a couple of days to enact, so they're not immediate. So let's look at some first results. On the left, this is the number of runs, and each run is simulating a year of the hospital running. The red line is the performance in terms of the reward, and you see it actually gets quite bad. It gets worse to begin with as it explores, and then after a bit it starts to learn, and it can learn, you see, pretty quickly. The performance comes back up, and then it settles off and stabilizes. And on the right, we see the last year of it learning, and the red line is the number of patients in the hospital, the green line the number of beds. And given its balance of rewards and penalties, it's come up with a way of acting that's got 94% bed occupancy. 92 days we didn't have sufficient beds. 270 days we had spare beds. And just to say, this particular agent is actually a multi-agent. There are 10 different learning agents, and we sample from the decisions each would make, and that gives us a natural exploration to begin with. When they haven't learned, they will start recommending different things, but as they learn, they start to settle on the same recommendation. So we get a natural shift from exploration to exploitation as the agents get better. And then finally, here's a paper reference in arXiv, and the link will be in the YouTube video below. Okay, thank you very much.